Hey, thank you, Cynthia and Kuno, for organizing this and for inviting me. It's my great pleasure to speak in front of such a great audience. So I will talk about a very cool topic in statistics and machine learning, Sparse PCA, and I will describe the structure of the problem and some exciting results, non-privately, and also I think I shall mention some connections and the way I think how this would fit into many different methods in differential privacy. And this is the statistical part of this work is based on my collaborators, Vince Wu, who is in the audience, and actually he should take a lot of credit for the statistical work on this project, and also with Juhi and Carl, our collaborators in Wisconsin. So this talk will have two parts. So the first part is the statistical part, Sparse PCA, and finally I will talk about the link between Sparse PCA and differential privacy. So the privacy part is based on my own imagination and immature thinking. So if you find anything in this part stupid or immature, blame me only, not my collaborators. Okay, I make that clear. All right. So the motivation for PCA is very simple, right? I have high-dimensional data IID, and I would like to do some linear dimension reduction using principal components analysis. So the very basic introduction to the general PCA, I have the covariance matrix, for the underlying population, and the PCA is simply given by the eigenvalue decomposition for the population covariance matrix. And we have lambdas, the eigenvalues ordered in decreasing rank, and the eigenvectors, the VIs. So the optimal d-dimensional dimension reduction, in some sense, is given by the projection matrix corresponding to the linear space spanned by the first d eigenvectors. Right. And the optimal instance, it reduces the expected L2 distance between the original vector and the projected vector. Obviously, we don't know the population covariance matrix, and we estimate it using the most natural estimator, the sample average, and we calculate the counterparts of the eigenvalues and eigenvectors from the sigma hat. So, and we just plug those in as our estimators for the eigenvectors and the projection matrix. And these are our standard estimators, and they have many nice properties in the low dimensional regime where P is fixed and you have a large sample. Right. Now, when the number of parameters or number of variables is large, in the sense that P over N converges to something other than 0, or even infinity, PCA can be inconsistent in very simple models. So we would like to do something else to take advantage of some structure in the data, and Sparse PCA is one of them. It offers simultaneous dimension reduction and variable selection. And it has better statistical properties, we will see later, and obviously better interpretability. So interpretability means in the ordinary PCA, if you have a large number of variables, so the linear projection may involve many of them. So you don't know which ones are more important and which ones are less important, and Sparse PCA automatically selects the important ones. So what do you mean by sparsity in the PCA problem, right? So here the sparsity, we want the sparsity notion to be rotation invariant, because there's identifiability issue of the eigenvectors. If we have eigenvalues with multiplicity higher than 1, then we cannot distinguish the leading eigenvectors up to some rotation. So whatever I define or I estimate shall be rotation invariant, because the real goal in PCA is to find the dimension reduction. So we shall focus on the projection matrix, and we assume the projection matrix has at most S non-zero rows, and S is much smaller than P. So the interpretation is the projection. If you want to do projection, you only need to look at those S variables. So here is a more detailed description of the structure of the model. So the sigma can be written in terms of the sum of two matrices. So the first part we call it signal. It has only a small S by S non-zero block. And the noise part basically contains everything in the corresponding to the remaining eigenvectors. Right. So what we want to do is to estimate this projection matrix, which is sparse. And when there is a gap between the D and the D plus 1's eigenvalues, this decomposition is unique. Right? We only want to separate the leading D and the remaining. So this is also a minimal condition we shall have just to uniquely define the goal we're after. So here is the first theorem we developed just to describe how sparsity interacts with other model parameters like lambda, D, and P in determining the hardness of the problem. So it says the optimal error rate of estimating the projection matrix in Frobenius norm is this. It's a simple function of 7 numbers, S, D, P, and lambdas. Right? And so it depends on the sparsity in a linear manner, and we have the D corresponding to the parametric rate. So if you have an oracle telling you those S variables are true, and we only have the S times D, so that's the low dimensional part. But here the log P comes from the need to select the relevant variables. So it took us quite a few months to figure out this sum D plus log P. And also, it's interesting to see the lambda D plus 1 here. That's another tricky part, because imagine if lambda D plus 1 is 0, then the data itself is in D dimension, so there is 0 error, right? And this minimax optimal rate is achieved by the sparsity constrained projection matrix and in the PCA problem, right? If we maximize this trace of sigma hat times pi over all d-dimensional projection matrices, that's the regular PCA, and we add a further sparsity constraint. Right. Yeah. A few sentences about the proof. So everything starts from the upper bound. The lower bound is actually two construction using Funnel's method, one on the P part and the one on the D part. So the upper bound, we start from curvature lemma, which is very cool. It's different from Davis-Kahan, and Vince shall take most credit for this. It says in the PCA problem, so this guy pi sub d is optimal, and this guy, our estimator, is suboptimal, and it bounds the gap in the objective function in terms of the difference. Right. So this is the curvature of the PCA problem, and the coefficient, the factor, is determined by the eigengap. So intuitively, very natural. And indeed, the proof of this one is elementary, but we didn't find it in previous literature. And on the other hand, we have the estimator optimizing the objective function using the estimated covariance matrix, and we combine these two, we entered this inequality. This part is our estimation error, and this part is actually can be bounded by an empirical process, because we hope this matrix is small. It's the random error part. And the rest is some careful analysis using empirical process and some other techniques like the peeling thing.
Sorry, Jing.
Yes?
I lost track. What what's sigma hat and sigma? What's the difference between sigma hat and sigma here?
Sigma is the underlying true covariance matrix. So it's determined by the distribution. And the sigma hat is estimated from the data.
Okay.
So the sample average minus the expectation, so it corresponds to some form of empirical process. So as I said, this theorem gives optimal dependence on all these 7 parameters. And it does not put any additional structural assumptions on the noise part. So it doesn't have to be even block diagonal. And a popular assumption is that it's spherical. The noise is spherical. But the downside is the proposed minimax estimator is NP hard to compute. So the next step we want to do is to do some convex relaxation. So here is our convex formulation. If you attended the NIPS, you probably have seen the poster. So we start from the standard PCA problem. That's the maximizing the trace between sigma hat and z. That's just the PCA part. And we put a penalty, L1 penalty. We choose L1 because it has this nice decomposability property. And what's really interesting is the constraint set, right? Remember, we used to assume that the z shall be picked from the set of all d-dimensional projection matrices, but that set is not convex. The tightest convex of d-dimensional projection matrices is this one. So z shall be symmetric and positive definite with all eigenvalue between 0 and 1, and the trace is d. So it can be shown, actually we didn't show this, we found this result in the literature. This is the convex of all d-dimension projection, and it's called the Fan top, named after the mathematician Key Fan. This problem is convex, and we think it's the tightest convex relaxation for PCA problem with sparsity. And it can be solved using standard methods like ADMM. It's really fast and convenient. Yes?
Probably stupid question. The one norm of z is just the sum of
Oh,
the entries.
treating z as a vector. So what can we say about this method? When the penalty term, the rho, is chosen, sorry, I made a typo. This should be log p. Right. Is proportional to square root of log p over n, then the Frobenius norm error of the output of FPS satisfies this. So it differs from the minimax rates in terms of the s square, and we don't have that d plus log p here. So roughly speaking, this square there is off by roughly by a factor of s, and we conjecture you cannot substantially improve this dependence for polynomial time algorithms based on the insight provided by the work by Bracet and Regulator earlier. They said if you are doing hypothesis testing, then polynomial time algorithms cannot distinguish like at the level of when S is beyond this range, assuming that the planted clique problem is hard when S is smaller than square root n. So that's true. That's established for the testing problem, and we think it shouldn't be too different in the estimation problem. And the proof is very short. Actually, this is the whole proof. We extend the curvature lemma to the Fan top. This is also due to Vence. And we use the same trick. Now we have the curvature lemma part, and the empirical process part, and the penalty part. And we don't do very hardcore analysis on the empirical process anymore because we don't know too much about the hat z. So then we use the fact that we have a L1 penalty and it dominates every entry in that error matrix. So we ended up with something very simple, and the following analysis is standard using triangle inequality and Cauchy-Schwarz. Well, so that's cool. And we have just one more question. We want to do variable selection, right? We don't know how sparse that FPS solution will give us. And even at the ideal choice of penalty parameter. So we hope, so basically everything is so similar to the lasso, right? And I think maybe we can do something similar in variable selection. And the problem, the variable selection problem for d equals 1 is analyzed in a simplified assumption by Amini and Wainwright a few years ago. So our result will focus on the fan top. So we were able to do two things. First, we are able to remove a common assumption, so which has been always there in previous work on variable selection in PCA. So the diagonal part of the noise matrix no longer has to be 0. Right? It just needs to be bounded by something, but it does not have to be 0. So we removed this block diagonal assumption, and we were able to do for general value of D. So that's the result. The FPS correctly selects the relevant variables when these 4 conditions hold, because we're doing more and more, so we have more and more assumptions. The sample complexity, which is similar to previous result, and the incoherence, right? Remember in the lasso, we want some incoherence to limit the dependence between the noise and the relevant variable, and here it is. It basically says, I have the covariance matrix, that's the signal block, and the big noise block, and this block, they're the same, right? And this block is gamma to 1, and it describes the correlation between the signal variable and the noise variable. And what I need is each row has bounded L2 norm, and the bound is proportional to 1 over S. And also, we need signal strength. The minimum diagonal entry of the non-zero part of the projection matrix is at least this large, and also the tuning parameter is okay. Right? And one remark is that the information theoretic lower bound developed by Amini and Wainwright is n at least S times log P, so there's also a factor of S off. And it's also an open question if this can be removed and in a polynomial time algorithm. And I just hide all the constants or all the eigenvalues into the constants. Right, so the key ingredients of this proof also, so the important part is we only need the infinity norm of the error. That means the entry-wise infinity norm of the error matrix to be small, and it used strong duality and KKT condition, curvature lemma again, and standard linear algebra and perturbation theory. Right, so it's a little bit more involved and don't have enough time to go through it. Now, so that's the statistics part. I want to talk about differential privacy, especially for the FPS algorithm. So starting from now, any mistake is on me. The analysis of FPS only needs to satisfy the entry-wise error bound. Right? What we really need is just the entry-wise error bound is on the order of square root of log P over n. And in the sample covariance matrix case, this follows from Bernstein and the union bound. So the first idea I had to do differentially private FPS is to further add entry-wise perturbations on the sample covariance matrix on the order of square root log P over n. If we can do that, then we're good. Okay, the first step, Laplace Noice, it doesn't work anymore, at least in the high dimension case. So the goal is I want to release the covariance sample covariance with entry-wise accuracy square root of log p over n. And for simplicity, I assume the data is bounded with zero mean. If I do this, the entry-wise double exponential, then the noise should be of order p squared over n because I have p squared entries. I change one row of the data, I change every entry at the same time. So this is a very naive idea, and we know it's not going to be the best one. So a further step forward, if we realize every entry of the covariance matrix, sample covariance matrix is just a sample average, and in the computer science literature, it's called counting query. And they are bounded, and it's just a sample average, so they are counting queries. And then if I use a result on differentially private counting query release, and this is the best one I know about. Maybe you can tell me if you know better ones. And I would be able to reduce the entry-wise error rate to this. But a potential downside is this theory developed in that paper applies to discrete space. And what I need here is uncontinuous space. But if my data is really discrete and bounded, then this would apply. So I'm curious if one can remove that extra log p to the 1/4. If we can do that, then it's almost match the best result in non-private analysis. Well, so the nice thing I liked about the PCA problem is you can attack it from different angles. The structure is so nice. The other method is to use the stability test, right? The perturbation stability in a paper by Adam and Abradeep. So we want to test how stable the variable selection result is, right? So I just ask how many points I need to move in my data set to obtain a different variable selection result. If that answer is large enough, then I proceed with the variable selection. So I'm working on a much smaller problem. Then things should be much easier there. And this is applied to lasso. Again, this is motivated partially by the similarity we have observed so far between the sparse PCA and the lasso. So if you can do it for the lasso, then probably for PCA. And the plan is we do the model selection first in DP, and we just release that small corner using another DP procedure. The rest is zero. But the challenge is the query itself is insensitive but maybe hard to compute. And my intuition on this, I didn't write it down because it's probably not true. It should be easier for PCA because PCA is not an inverse problem. So we don't need to do the X transpose inverse in PCA. Everything in PCA is just sample average. So I expect the query is easier to find in PCA. And there's a third method. If I just write this in the matrix form, then it's not sample average anymore, but matrix product. And every entry in the sample covariance measures the covariance or correlation, or in some sense the similarity between the variables, not the individuals. But it doesn't matter. We can switch the role between the variables and the individuals. And it's known by these two groups. The papers appeared at about the same time. Johnson-Linden-Strauss transform. Like basically you multiply the matrix by a random matrix with IID Gaussian. Then the pairwise similarity is roughly preserved. And at the same time, you almost automatically have differential privacy. So the idea is to use sample covariance of a perturbed version, so R times X, optionally plus an addition noise matrix, and then we just go from there. So the challenge would be to develop a good bound. So for the purpose of PCA, right? We only need the entry-wise error. So how do we optimally choose R or delta, so that the y is as accurate as possible. So my hope is, and I think it's true, in the regime the FPS algorithm works, the solution should be very stable, and we shall be able to do all these. But the problem is, which one shall I choose? Which method is most suitable for this sparse PCA problem? And that's like, I'm actually a statistician and a user of differential privacy, so I need some help to choose the right product. So the final message, PCA, sparse PCA, very interesting problem, lots of good structure, so that should be the favorite toy for theorists. And the current analysis fits very well in quite a few frameworks of DP. And there are some technique I'm particularly interested in. The accurate release of p-square related, because the entries of covariance matrix, they are not independent. They are related in a tricky way. Counting queries in continuous space, and stability test for PCA, and maybe if we find some structure and we can generalize it to more general settings, and private Johnson-Linden-Strauss for the PCA problem, and even a DP ADMM. I really don't have any idea on this, but if we can do that, that would be really, really cool. So, all right, I'm 2 minutes over time, so that's. Thank you for your attention.
What was ADMM again?
Alternating direction method of multipliers. It's a class of convex optimization algorithm. So it's very cool for problem where you have multiple constraints. So here we have the fan top and the L1 ball. So it's hard to find out the intersection between these two, but the ADMM gives you like some quick way for initial convergence.
So what do you mean DP ADM?
Differentially private version of ADMM.
Yeah,
So
what does this mean?
that means I have an input to ADMM, and for any generic input and generic ADMM method, can I tune, say, the step size in ADMM in a differentially private way, so that the output is automatically differentially private? Well, assuming, of course, changing one data point only changes the input structure in a simple manner. Right, but you can do a differentially private stochastic gradient descent, right? That's another class of optimization method.
So, in joint work with Cynthia, Lee, and Abhijit, we made some improvements on the first approach, and I'll talk about it tomorrow. So I think
Tomorrow?
actually, yeah.
Okay.
So you
I
can
will look at the video.
with very little
Yeah.
Wait, but
noise.
there's a normalization issue. So he was bounding just the L infinity norm of the raw data, right? Whereas you guys bound the L2 norm of the input
No, I think here
vectors.
also he's bounding the L2 norm of xi.
Didn't he say? I thought the assumption was just that they were the entries of the xi's were
The
bounded.
entry of the sample covariance. It's not the xi's themselves. So it's actually a collection of counting query.
Okay, yeah. Anyway, I guess it depends on how things are normalized, right?
Right.
How well that idea will work.
So your assumption is that each xi is mean zero, norm at most 1?
Not norm at most, but every entry is at most.
Oh, every entry is at most 1. I see.
So
I think we'll probably still be fine. So the
You
norm
still
is at most
probably save a factor of p,
square root
but
p.
not-
Okay.
Not log p.
Okay, thanks, Jing.
Thank you.